Before we start talking about Stirling numbers, let's say a few words about James Stirling, who was a Scottish mathematician, nicknamed the Venetian. If you want to find out more about his life, you can look it up on Wikipedia or a MacTutor archive of mathematicians. Stirling had quite an interesting life, and you can read about the reason why he was nicknamed the Venetian. So around 1730, he published his most important work, Methodus Differentialis, and in it, it contained this formula approximating the value of n factorial. So it states that n factorial is about n over e to the power n times square root of 2 pi n. And the notation that we use will say that two functions defined on the set of natural numbers, f and g, are approximately equal if the limit as n goes to infinity of the ratio it is 1. Now, Stirling formula, his name is attached to this formula nowadays, but this formula was known around the same time to the French mathematician Abraham de Moivre. Now, we won't discuss more about Stirling formula. I just wanted to say that it can be proved using approximation of the area under the curve of natural logarithm of x with x between 1 and n, using Riemann sums involving trapezoids and so on. Let's talk now about the Stirling numbers. And Stirling numbers of first kind have a bit of an unusual definition, but it's not too difficult once you get used to it. So first of all, they are defined, let's say we have two natural numbers n and k, with n greater or equal to k. And the absolute, first let's define the absolute value of the Stirling number s and k is by definition the number of permutations in Sn that have exactly k disjoint cycles in their decomposition. So this is the absolute value of the Stirling number of the first kind, and the Stirling number of the first kind is actually defined as a signed version of this number, and S and K is defined as -1 to the power n minus k times this absolute value of S and K. We'll see in a second when we prove some of the properties of the Stirling numbers, the reason of this definition. Now, I want to talk a little bit about the definition. We have exactly k disjoint cycles in their decompositions. So we proved earlier in the class that every non-identity permutation can be written as a product of pairwise disjoint cycles. And for us, we always consider a cycle to have at least two elements. So the cycle will be like something like a transposition and so on. Now, in this situation, we will consider a fixed point of a transposition to count as a cycle of length 1 in its decomposition. So let's do some examples to see what we mean by this. So let's say, for example, n equals 3. And let's say we have the permutation in a two line 1, 2, 3, 2, 1, and 3. And this is a transposition 1, 2 in our notation. But this permutation is considered to us to be, so sigma for us will be a permutation in S3. And we will say that sigma has exactly two disjoint cycles. Namely, the cycles will be 1, 2, and we'll consider 3 by itself as being a cycle. So with that notation in mind, if we look at the permutation epsilon, the identity in Sn, the identity permutation, So this permutation has n disjoint cycles in its decomposition. And it's actually the only permutation that has this property, so that leads to the fact that S and N equals 1. Actually, the absolute value of S and N equals 1, but even if you take into account the sign, you get that S and N equals 1. Okay. So what other values of this Stirling number can we find? Well, let's go to the other end. If we look at S and 1, let's say in absolute value, this is a number of permutation in Sn that have exactly one cycle in their decomposition. So this is the number of circular permutations on an element, and this is n-1 factorial. And with the sign taken into account, we get that Sn1 equals -1 to the power n-1 times n-1 factorial. And I'll do one more quick example. What is Sn n-1? Well, if we have a permutation on n elements, and we have n-1 cycles into that in its decomposition, disjoint cycle in its decomposition, then n-2 of them are going to be fixed points, and one of them is going to be a transposition. So this is the number of transpositions, which is n choose 2, and that leads to Sn n-1, it's minus n choose 2. Okay, so now let's look at these numbers in more detail and see what we can say about them. So we'll prove a couple of things about the numbers. So the proposition, if n is greater or equal to k are natural numbers, then we'll prove A, the absolute value of Sn plus k plus 1k equals n times the absolute value of Snk plus the absolute value of Snk minus 1. And B will be an immediate consequence of this result, be that Sn plus 1 k equals minus n Snk plus Snk minus 1. So we'll prove part 1, and we'll use part 2. I'll leave the implication for part A to part B as an exercise for you. And we'll use part B later on to discover another interesting property of these numbers. So again, this is a recurrence relation. The Stirling numbers depend on 2 parameters. And so we will prove part A. Okay, so to prove part A, let's look on the left-hand side. So the left-hand side of the equation, it counts permutation sigma in Sn plus 1 that have exactly k disjoint cycles. Now these permutations, let's split them into 2 parts. In one part, let's put the ones where they map n plus 1 to n plus 1. So n plus 1 is a fixed point. And the other ones are going to be the ones where n plus 1 is not a fixed point. So clearly, so left-hand side counts all these permutations sigma. And clearly, this is a partition of this set of permutation with exactly k disjoint cycles. And we'll count each of these two parts of our partition. Now, on the first part, our permutation sigma looks like 1 to n, and n plus 1 is fixed. And here we have sigma 1, sigma 2, sigma n. And now we could just ignore this part. Okay, so n plus 1 is fixed, so it participates into one cycle, what we consider one cycle of length 1. Therefore, if we look at the permutation sigma prime, which is in Sn, which is sigma prime of j equals sigma of j for any j between 1 and n, what type of permutation is this one? So it's a permutation on n letters, and how many cycles, disjoint cycle, does it have in its decomposition? Well, the original permutation sigma had k cycles, and one of them was this fixed point. So this permutation sigma prime has k minus 1 disjoint cycles. And how many such permutations are there? Well, that's the absolute value of Sn k minus 1. Okay, so that's not too hard. What happens on the other side? Well, in this situation, our permutation sigma, it has a bunch of cycles, and m plus 1 is in one of these cycles. So it has 1, 2, 3 k cycles. Like I said, these cycles could be fixed points, or could be cycles of length 2 and so on. Okay. In this situation, we'll do something similar. We'll reduce this the count of this permutation sigma we'll relate it to counting permutations on n letters. And how are we going to do that? Well, here's how it goes. If we have this permutation sigma with n plus 1 in a cycle, if we ignore the n plus 1 in that cycle, we get a permutation, let's call it S double prime, which looks exactly as sigma, except that S double prime is in Sn and it has k disjoint cycles. So you just ignore that the n plus 1, and if you had here an element x that was mapped from by the permutation to n plus 1, and n plus 1 was mapped to y. So here x and y could be the same. So there's at least, because n plus 1 is not fixed by the permutation sigma, there is at least one such x in the same cycle with n plus 1. So in that situation, in the permutation sigma prime, what we will do is we'll just map sigma x to y and keep the remaining part of the cycle the same in sigma double prime as it was in sigma. So this gives us a correspondence from our permutation on n plus 1 elements with k disjoint cycles to this permutation on n elements with k disjoint cycles. But how about backwards? How does the correspondence go from this permutation sigma double prime to the permutation sigma? Well, such a permutation sigma can be obtained by taking a permutation sigma double prime on k disjoint cycles and inserting n plus 1 in one of these cycles. Now, in how many ways can you insert n plus 1 into these cycles? Well, if you have a cycle like the one involving the second cycle here, 2, the one here, then n plus 1, there's exactly one place where you insert n plus 1, and n plus 1 and the previously existing element, fixed element in that cycle, become a transposition. So there's one way. Let's look at a different picture. If we have the transposition here on this first cycle, and we can insert n plus 1 here, or you can insert n plus 1 here, and you get different permutation. So one can see that if you have a cycle of a certain length, let's say L, there are L places to insert n plus 1. And if you do the count, it's not hard to see that there are actually n places to insert the element n plus 1 into one of these permutations sigma double prime of Sn with k disjoint cycles to obtain a permutation that we have here on n plus 1 elements with k cycles that doesn't fix the element n plus 1. So the count in this situation is going to be n, which is the number of places you put in n plus 1, times the number of such permutations sigma double prime, which is s and k. And so the left-hand side in our equation above will equal the sum of these two things. And that's exactly part A of our proposition. And again, part B, I will leave you to figure out this implication as an exercise. Okay. All right, so now we can use that recurrence relation. Let me write it one more time. So the B recurrence relation, I'll write it one more time here. Minus n. Okay, and we'll use this relation, result to prove the following proposition. Let n be a natural number and t be a real number. Then, if we write the following factorial, I'll define this in a second. T following factorial n. And if we're expanding this according to the powers of t, this will equal, the coefficients will be the Stirling numbers. This will be summation from k equals 1 to n of s and k t to the k. So let's, before I give the proof, let me define this t following factorial. We've talked about it before. So t following factorial n will be a product of t factors starting with t minus 1, t minus n plus 1. So these are n factors. Okay, so for example, t of 1 is t, and by convention we can say that t0 is 1, and then t2 is t times t minus 1, and this equals t squared minus t, and similarly t3 is t times t minus 1 times t2, and is t cubed minus 3t squared plus 2t, and so on, you know, t to the following factorial n, it will be like a t times t minus 1, t minus n plus 1. And the coefficient of t to the n is pretty easy to figure out, that's 1. But then you'll have something times t n minus 1, let's say plus, and so on, plus something times t. And our result here on the top states that these coefficients are actually the Stirling numbers of the first kind. Okay. Now, let's prove this result. To prove it, we will use induction on n. So for the base case is n equals 1. And in that case, the left-hand side is t. And what is the right-hand side? The right-hand side is n is 1, so it's s1, 1, t to the power 1. There's only one permutation with one cycle on one element, so that's t. So t equals t, so that is correct. The base case is correct. Now, for the induction step, assume that our statement is true for n, for some n natural number. So what does that mean? That means that we know that t n following factorial is the summation from k equals 1 to n S and K times T to the K for any T real number. And now what do we want? We want to prove that the statement is true for n plus 1, meaning we want to show that Tn plus 1 equals sum from k equals 1 to n plus 1 of Sn plus 1 k T to the power k for any T real. So how do we go about proving the red equation? Well, we start with the equation that we know, okay? So let's first take T, a real number, and from our induction hypothesis, we know that Tn is the sum from k equals 1 to n Sn k T to the power k. Okay. So what do we do here? Well, we are going to multiply both sides by T minus n. And the reason for doing that is that when we multiply both sides by T minus n, the left-hand side will become the following factorial that we want on the red equation. So we multiply both sides by that T minus n, and again, I'll write it here. Note that if I take Tn and I multiply by T minus n, this is T times T minus 1 times T minus n plus 1 times T minus n, and this is exactly this Tn plus 1 following factorial. So we will have, from this multiplication, on the left-hand side, we'll end up with what we want in the red equation, but on the right-hand side, we are not going to have exactly what we want. So let me write this. It will be summation from k equals 1 to n of S and k tk. So let's just do the multiplication once. Tk plus 1 minus n tk. Okay. So let's rewrite what we have. We have this on the left-hand side, and on the right-hand side, we have a sum from k equals 1 to n of S and k tk plus 1 minus n tk. Now we split the sum into two parts. So on the first one is the sum from k equals 1 to n of S and k tk plus 1 minus, on the second we have the sum from k equals 1 to n of n S and k t to the k. And to make it easier now, to combine this sum back again, we change the index for our summation. We replace our k plus 1 by the index k. So when k goes from 1 to n, k plus 1 will go from 2 to n plus 1, and this will be S of n k minus 1, and this is going to be 2 to the k, and here minus, we just copy the thing from above. If this change of summation is complicated, just use different letters. Just on the second sum, just instead of k, just use L. Write L as being k plus 1, and replace the k from the first sum in terms of L in the second sum. But I hope it's clear as it is. Now, what do we get? So the first sum has a power that the second one doesn't, and I'll write that explicitly here. That's going to be S n n, that is when k equals n plus 1. So I will have s n n, t to the n plus 1. Then I will combine here the terms that have t to the power k, where k goes between 2 and n in both sums. So that I will have an s n k minus 1 from the first, and I will have a minus n s n k from the second, times t to the k, plus what's left, it's actually a minus, there's a k equals 1 from the second sum, and that's going to be minus n s n 1 t to the power 1. Now, what is s n n? S n n is, we calculated earlier, is 1, and it's the same as s n plus 1 n plus 1. Okay. Now, what do we have in the second? In the sum, we have a sum from k equals 2 to n, but this expression here is exactly the right-hand side of the part B of our previous proposition, and this is going to give us Sn plus 1 k, t to the power k. Very good. And now we have one last thing to deal with in the end. And if you remember, Sn1 was the number of circular permutations, and that was something like minus 1 to the power n minus 1 times n minus 1 factorial. When it combines to that minus sign from the end, I'll leave it to you to as an exercise to figure out that what we get is plus s n plus 1 1 t to the power 1. And now this is exactly what we wanted. This is a sum from k actually equals to 1 to n plus 1 of s n plus 1 k t to the k. So this proves our conclusion here for the induction step, and it proves our general result. Now, there are some people who introduce the Stirling numbers by this equation, saying that S and K are the coefficients of this in this decomposition, and then you can go ahead and prove all the other properties and deduce that S and K is what we consider to be the definition here, the number of K disjoint cycles. Okay, so these properties are in a sense equivalent. Okay, so this is these are some properties of the Stirling numbers of the first kind. So let's move to the Stirling number of the second kind. As before, we have two natural numbers n greater or equal to k. And we use capital S here, S and K. This is the Stirling number of the second kind, is defined as the number of partitions of the set with n elements, n. Recall this is the set of all elements from 1 to n, into k parts or blocks. And when we say partition, these parts and blocks are assumed to be non-empty. Okay. So this is S and K. So if you have n elements, obviously you cannot partition them into n plus 1 or more element parts. So that's why you have always n greater or equal to k. In that situation, when k is bigger than n, you can say that S and K equals 0. So let's do some examples. What will be S and 1? Well, that's number of partition of n into one part, and that's just the set itself. So this is 1, so that's pretty easy. And then at the other end, what is S and n? Number of partitions of the set n into exactly n parts, and that is also 1, because there's only one partition. Now let's do something a bit more, a bit harder. Let's say the partition into 2 parts. Well, when we have a partition into 2 parts, we have our set n, And it's a union of, let's say, A1 union A2. So I put the dot on the top to represent the fact that A1 intersect A2 is an empty set. Now, you see here that A1 determines A2. So this is the same thing as A2 is n minus A1. So it's enough for me to count the number of A1s. So what property does A1 have? Well, A1 cannot be the empty set. At the same time, A2 cannot be the empty set. So that implies that A1 also cannot be the whole set n. Okay. So we have, in general, we have 2 to the n subsets of the set n. And we have 2 of them that cannot happen. So -2. So that's how many choices we have for A1. But for us, when we consider the partition A1, A2, this is the same as the partition A2, A1. Okay, so the number of partitions will be the number of choices for A, but we have to divide by 2, and we will get 2 to the n minus 1 minus 1. And this is the answer here, 2 to the n minus 1 minus 1. This is Sn2. The number of, in some sense, you can say unordered partitions. So when we say the number of partitions here, I guess you can assume that they're unordered partitions. So that gives us 2 to the n minus 1 minus 1. And with that in mind, we can also interpret S and K as follows. Let me give you another interpretation. And this will be the following, that if I look at S and K, and I shuffle all the blocks of the partitions, and that's, let me do a red. That can be done in K factorial way. K factorial times S and K, this equals the number of surjective functions F, let's say, from the set with n elements to the set with k elements. Okay, how is that? So this is a proposition, so it requires a proof. Okay. Well, if I take a partition, so let's take a partition N, which is A1 union blah 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 union AK, or again, all these A1, A2, AK are disjoint. Then I can make a function F from N to K that is surjective as follows. I can define the pre-image. So I can say that the pre-image of the element 1 yes, will be the set A1, and so on. The pre-image of element K will be the set AK. So if we think about it as a picture, we have here the set N, and here let's say we have A1, we have A2, we have AK, and here I have the domain K, and here I have the element 1, element 2, say the element K, like this. And the function that I described there sends every element from A1, it maps them here to 1, every element from A2 maps it to 2, every element from AK maps it to K. Okay, so that's one function that I can make. But I actually can make K factorial such functions from a single partition, because I can take any permutation of 1 to K, so I can take any permutation sigma in SK, and for that permutation I can make a function in which I say that the inverse of let's say of 1 is a sigma 1, and so on, if the inverse of k is a sigma k. And this is also a surjective function, and it's a different function than the one, if the permutation sigma is different from identities, is a different function from the function f. So we call this one f sigma that I just described there. And that corresponds to shuffling this, instead of sending a1 to 1 and so on, you can decide to send a1 to something else, a2 to 1, and so on. So you can shuffle this correspondence between a1, a2, ak, and 1 to k in k factorial ways. So backwards, any surjective permutation will arise this way. So again, from this permutation, we will get k factorial surjective functions from n to k, and backwards, any permutation, any surjective function from the set with n elements to a set with k elements comes from such a partition, because if a function is surjective, the preimages of the elements 1, 2, 3, k form a partition of the set n. Now, yeah, this is nice, and I'll write here the formula. So let me write below here the formula that we obtained when we used principle of inclusion and exclusion, and we actually calculated the number of surjective functions. So that will give us, if we apply that formula, we will get that k factorial times Sn(k) equals a summation from j equals 0 to k of k, choose j, minus 1 to the power j, k minus j to the power n. So you can call it explicit formula for Sn(k), although it may not be entirely satisfactory because it's an alternating sum, so it may be tricky to figure out how quickly this function Sn(k) grows from this formula, but it's a very useful formula nevertheless. Okay, now let's prove a couple of more things about this function, about these Stirling numbers. I'm sorry. The first proposition is a similar proposition to the recurrence relation that we had before. Let n and k be two natural numbers. Then we can represent Sn plus 1k in terms of Sn(k) minus 1 and Sn(k). And it's a similar formula, but it's different from the previous one. So how do we prove it? Well, as before, Sn plus 1k counts the number of partitions of n plus 1 into k blocks. Okay. And now we split this partition into two kinds. In the first type of partition, we'll put the ones where n plus 1 is a singleton block. So n plus 1, the set n plus 1, is one of these sets a1, a2, a1, a2. Let's just say, for simplicity, ak is n plus 1. So in that case, what happens? Well, in that case, clearly n will be the other sets, a1, a2, ak, will form a partition of the set n, and every partition of n plus 1 with this property that n plus 1 is a singleton block arises this way. Now, how many partitions do we have here of this form? Well, we have S and K, such partitions. Well, yeah, we have to be a bit careful because there's one mistake here. When we get rid of AK, this is AK minus 1. So we have S and K minus 1, such partitions. Now, in the other situation, n plus 1 is not a singleton block. So in this situation, let me draw it this way. Let's say we have A1, we have A2, we have AK, and let's say n plus 1 belongs to AK. There's n plus 1 there, but there are also other elements in there, at least one other element in there. Okay. Now we can do something similar. So in this situation, from that partition of n plus 1 into k parts, we can get another partition, but in which we ignore, we take away. So this part with n plus 1, we throw the n plus 1 away, and we have here, let's say, a prime k, which is ak minus n plus 1. And because ak was not a singleton, this a prime k is not empty. So this here, a1, a2, ak minus 1, a prime k, this is a partition of n into k blocks. Okay, so that's one direction. What about backwards? In how many ways can we get such a permutation, such a partition, this property? Well, we can take, if we have a partition of this kind, of the one at the bottom of n into k parts, they're s and k such partitions, then we can insert n plus 1 in any one of the k blocks, and we get a partition with of n plus 1 into k blocks where n plus 1 is not a singleton. So the number of partitions in this situation is going to be SNK times k. So this is the number of such partitions, and that gives us the recurrence relation that we wanted. Okay. Now, with this in mind, we can prove a similar result to the second result that we had for the Stirling numbers of the first kind. So we have n a natural number and t a real number. Then, now we're going to go backwards. Instead of expressing the following factorial in terms of the powers of t, you want to express the powers of t in terms of the following factorial, and it turns out that we can do that, and this will equal the summation of k from 1 to n of SNK times t following factorial k. Okay, so let's prove this result. Again, we use induction on n. So for the base case, n equals 1, and our left-hand side, the equation above, is t to the power 1, which is t. Now, what is the right-hand side? So n equals 1, so that will be S11 T1. And S11 is 1, partition of set with one element into one block, and this is t, so it equals t, so this is correct. Now for the induction step, assume the equation above is true for some n, natural number. So we have that t to the power n is the summation from k equals 1 to n of S and k t following factorial k. We prove, or we show that it is true for n plus 1. So this statement is the statement for any t real number. So we will show that t to the n plus 1 equals the summation from k equals 1 to n plus 1 s n plus 1 k t following factorial k for any t real number. So the proof is similar to what we did earlier. Namely, we'll start with the first part. So let t be a real number. And we start with the first part. We know that t to the power n is the summation from k equals 1 to n plus 1. Now, our goal is to get to this red equation, and so it's fairly easy to see that to get from t to the n to the left-hand side on the red equation, t to the n plus 1, we have to multiply by t. So we'll take this equation here, and we'll multiply both sides by t. And what do we get? We get t to the n plus 1 on the left, and this will be summation from k equals 1 to n, Sn k t following factorial times t. Now the trick is to merge this t into this t following factorial k, and this is the trick. You write it, summation of k equals 1 to n, Sn k t following factorial k, and we write our t as t minus k plus k. Because t minus k merges very well into this product of t following factorial k. And what do we get? We get summation from k equals 1 to n, S and k. Now, this, let's just write it like this, t following factorial k times t minus k, plus, I'll write it as a separate sum, summation from k equals 1 to n of S and k. There is a k there, so k times t following factorial k. And the first sum becomes summation from k equals 1 to n, S and k, t following factorial k plus 1, plus summation from k equals 1 to n, S and k. It's a k in front, t following factorial k. Same as before, we change the sum, so it's a sum from k equals 2 to n plus 1. So I have S, n, and this will be k minus 1, and this will be tk, plus summation from k equals 1 to n, k, s, and k, t following factorial k. And now we keep the first one up. When k equals n plus 1, we have s and n, t following factorial n plus 1, plus now from 2 to n, we combine the terms in these two sums that have t following factorial k in them, and we'll have, let me write it here so I have space. We will have s and k minus 1 plus k, s, and k, and then t following factorial k, plus the last one is k equals 1, so we have s and 1, t1. And here, if we use the recurrence relation that we proved earlier, this part will be replaced by s plus n plus 1k. This part, partitioning of n parts into n parts is 1. It's the same thing as s n plus 1, n plus 1. And here, partition of a set with n elements into one part, it's 1, and it's the same thing as sn plus 1, 1. So we get summation from k equals 1 to n plus 1 of sn plus 1k, t following factorial k. And that proves it. So that's very nice. Let me give you one last thing that relates the Stirling number of first kind to the ones of the second kind. So this is a corollary of these results. And let's say we have the matrix n, a natural number, and we define two n by n matrices, A and B, as follows. Aij is the Stirling number of the first kind, Sij. So again, remember that in the situation that I is strictly less than j, this is 0. And similarly, we do Bij as capital of Sij, Stirling number of the second kind. Then these matrices are inverses of each other. A minus 1 is the inverse. The inverse of A minus 1 is B, or if you want to write it differently, AB equals IN. And the proof comes from what we did before and a bit of linear algebra. We look at the following vector space, the vector space of all polynomials in T that have degree at most n. So you have a n, t to the n, and they have no free term. You can include the free term if you want, but this is fine as it is. So a1, an, a1 real numbers. So this is a vector space over R, and the dimension of it is n, and you have one obvious basis, which is t to the n all the way to t to the power 1. But there is another basis, I'll leave it to you as an exercise. There is another basis of these falling factorials, t falling factorial n all the way to t to the t falling factorial 1. And the matrices A and B are the matrices obtained when you change bases. When you change bases from the basis of t to the n all the way to t1 to this falling factorial and backwards. And you know from linear algebra that when you change bases, the matrices multiply. So if you change bases twice in this situation, you'll get that A and B are inverses of each other. Okay, so I will stop here for today.